So now what we can do with this is we can check the interval of convergence for this representation of cosine. So we're going to use, or we're going to check convergence with the ratio test. And so if we look at the limit as n goes to infinity of a sub n plus 1 divided by a sub n, we get that this is the limit n goes to infinity. Well, if we take the absolute value, the minus 1 to the n's will go away, and so it's a sub n plus 1, which is x to the 2 times n plus 1. We have to be careful. We have to put n plus 1 in for n in parentheses, divided by 2 times the quantity n plus 1, which is going to ultimately to 2n plus 2, and I guess I could put that in the exponent of x. If we distribute the 2, we get a 2n minus 2. And then times the reciprocal of a sub n, which is 2n factorial divided by x to the 2n. And I'll put absolute value, even though, put absolute value. And so this equals, if we simplify, a limit as n goes to infinity. So in simplifying here, we get an x squared in the numerator. Okay, so we have an x to the 2n plus 2 divided by an x to the 2n, and the canceling leads to a subtraction of the exponents, which is x squared, and then the factorials will cancel where the 2n factorial will cancel almost everything that's in the denominator except for a 2n plus 2 and a 2n plus 1. So now if we take a limit of this guy, as n goes to infinity where x is fixed, this is equal to 0. So our Taylor series for cosine, it converges for all x. Okay, with its radius of convergence is, of course, infinity. And so this series representation converges for all x. And one thing that we can do with this series that's actually interesting is, what if we want to come up with a Taylor series for cosine of x squared? Okay. So this is our function, f of x equals cosine x squared. If we wanted to go by the definition of the Taylor series, we would compute derivatives. If you notice, the derivative of this function, cosine x squared, requires chain rule within chain rule. For instance, if we differentiate the cosine, we get a minus sine of x squared, but then we have to multiply by the derivative of what's inside, which is 2x. And you can see that just by taking the first derivative, computing a second derivative will require chain rule, product rule, and things just get messy from there. Okay, and so then we can actually use the previously obtained Taylor series to find the Taylor series for cosine of x squared. And what can we do? Well, we simply just plug in x squared in for x. So the Taylor series centered at c equals 0. So let me make sure that's clear. So I'll say Taylor series for cosine of x squared centered at c equals 0. And it's quite simply just plugging in x squared. And we can do this because our representation of cosine converges for all x, and we're not concerned with values of x where our Taylor series does not converge. So if we plug in x squared in for x, we have a minus 1 to the n, and then x to the 2n. So if we plug in x squared in for x, and then now raise this to the 2n, and then divide by the 2n factorial, well, I'm going to, since I'm out of board space here, well actually I'll go to the next board. We simply get that the cosine of x squared equals a series from 0 to infinity minus 1 to the n x to the, so let's see, we take a product of 2 and 2n, so we have x to the 4n over 2n factorial. And so it's just as easy to look at our representation of cosine written out in the terms, and if we plug in x squared in for x, we get a 1 minus, remember it was x squared over 2 factorial, which would now be an x to the 4th over 2 factorial, and then minus an x to the 8th over 4 factorial. So let me fix my 8. And then plus, I apologize, okay, so let's see, plus x to the 8th over 4 factorial. And let me erase this plus sign here. And then minus x to the 12th divided by 6 factorial plus more stuff. Okay, so there are times where we can we'll get around using the formula for computing a Taylor series, such as this case.